In the silent depths of space, where darkness stretches endlessly, something extraordinary happens. A star is born, not with a roar, but with a quiet, almost invisible spark. A celestial body begins its life. This moment, hidden from our eyes, is one of the most powerful events in the cosmos. Yet, it's not just about the birth of a star, it's about the birth of everything. Stars are the architects of the universe, the creators of light, and the very reason we exist. Today, we're diving into the fascinating story of how stars ignite, unraveling 10 intriguing insights into the birth of these cosmic wonders. From the collapse of vast gas clouds to the incredible forces of nuclear fusion, we'll explore the science, the mystery, and the beauty behind star formation. Why does this matter? Because without stars, there would be no galaxies, no planets, and no life. So, let's take a closer look at how these celestial powerhouses come to life and shape the universe as we know it. Ready to uncover the secrets of the stars, let's begin. Deep within the vast expanse of space, hidden from the naked eye, lies the birthplace of stars' molecular clouds. These colossal structures, often spanning hundreds of light years, are the cosmic nurseries where the story of star formation begins. Imagine a colossal, swirling ocean of gas and dust, so dense that it blocks out the light from distant stars. Within these clouds, the raw materials of the universe, hydrogen, helium, and trace amounts of heavier elements, are scattered like cosmic ingredients waiting to come together. But how does this chaotic sea of particles give rise to something as magnificent as a star? The answer lies in the delicate interplay of gravity and time. Over millions of years, these clouds begin to collapse under their own weight. Gravity, the silent sculptor of the cosmos, pulls the gas and dust inward, creating denser clumps within the cloud. Think of it like a cosmic game of tug-of-war, where gravity slowly wins, drawing the material closer and closer until it reaches a tipping point. Yet, gravity doesn't act alone. Turbulence within the cloud, along with external forces like shockwaves from nearby supernova, can trigger the collapse of these clumps. It's as if the universe itself nudges these regions, saying, "It's time." Once a clump reaches a critical density, it begins to heat up and the process of star formation truly begins. What's fascinating is that not all clumps become stars. Some may fragment further, giving rise to multiple stars, while others might dissipate back into the cloud. But for those that succeed, the journey from a cold, dark pocket of gas to a blazing star is nothing short of miraculous. It's a reminder that even in the emptiness of space, there's a rhythm, a process, and a purpose. And it all starts here in these cosmic nurseries where the seeds of starlight are sown. As the molecular cloud begins its slow, inevitable collapse, one force takes center stage: gravity. Though invisible and silent, gravity is the master sculptor of the cosmos, the unseen hand that guides the birth of stars. Picture it like this: a vast, diffuse cloud of gas and dust drifting aimlessly through space begins to feel the pull of its own mass. Over time, this inward tug grows stronger, drawing particles closer and closer together. But gravity isn't just pulling randomly, it's working with precision, compressing the cloud into denser pockets of material. As the cloud contracts, something fascinating happens. The gas within it starts to heat up. This isn't just a slight warming. It's a dramatic rise in temperature caused by the energy released as particles collide and press closer together. The core of the cloud becomes hotter and denser, a fiery seed at the center of what will one day become a star. This process, known as gravitational collapse, is the first critical step in star formation. Without it, the universe would remain a cold, dark expanse devoid of light and life. But gravity doesn't act in isolation. Two other key players help shape the journey from cloud to star: magnetic fields and turbulence. Magnetic fields thread through the cloud like invisible threads, influencing how the gas moves and where it clumps. They can slow down the collapse in some areas while allowing it to accelerate in others, creating a complex dance of forces. Turbulence, on the other hand, adds a chaotic element to the mix. Think of it as the cosmic equivalent of a stormy sea, with waves and eddies stirring the gas and dust, breaking it into smaller fragments and shaping its structure. Together, these forces create a delicate balance. Gravity pulls inward, while magnetic fields and turbulence push and pull in different directions, sculpting the cloud into a dynamic, ever-changing landscape. It's this interplay, this cosmic tug-of-war, that sets the stage for stellar ignition. Without it, stars might never form, and the universe as we know it would be unimaginably different. So, the next time you look up at the night sky, remember this: every star you see began its life in a similar dance of forces, a delicate balance of gravity, magnetism, and chaos. It's a reminder that even in the vast emptiness of space, there's an intricate order, a rhythm that shapes the birth of light itself. And it all starts with gravity, the invisible sculptor of the universe. As the collapsing cloud of gas and dust reaches its densest point, a remarkable transformation begins, the birth of a protostar. This isn't yet a star as we know it, glowing with the fiery light of nuclear fusion, but it's the cosmic equivalent of a newborn, full of potential and energy. At the heart of the collapsing cloud, a dense core forms, growing hotter and more compact under the relentless pull of gravity. This is the protostar phase, a pivotal moment in the life of a star, where the foundations for its future brilliance are laid. Think of a protostar as a cosmic ember glowing faintly as it gathers strength. It's surrounded by a swirling disk of gas and dust, feeding it material like a celestial buffet. Over time, this young star grows larger and hotter, but it's not yet ready to shine. Why? Because the temperatures at its core haven't reached the critical point needed to ignite nuclear fusion, the process that powers fully formed stars. Instead, the protostar radiates energy from the heat of its contraction, a slow but steady buildup of pressure and temperature. What's fascinating about this phase is the sheer amount of energy involved. Even without fusion, the protostar is a dynamic and active object. It's not just sitting quietly, it's pulling in material from its surroundings, accreting mass and growing stronger. Sometimes this process can lead to dramatic outbursts, as excess material is ejected in powerful jets of gas, shooting out from the protostar's poles. These jets, often visible to astronomers, are like cosmic fireworks, signaling the intense activity happening within. But the journey from protostar to star isn't a straight path. It's a delicate balancing act. The protostar must gather enough mass to sustain fusion, but not so much that it disrupts its own growth. Too much material too quickly, and the protostar could fragment or even collapse under its own weight. It's a cosmic tightrope walk where every step matters. As the protostar continues to grow, its core temperature rises, inching closer to the threshold needed for fusion. Once it crosses that critical line around 10 million degrees Celsius, nuclear reactions will ignite, and the protostar will officially become a star. But until then, it's a work in progress, a celestial masterpiece in the making. This phase can last anywhere from tens of thousands to millions of years, depending on the size of the star and the conditions of its birth. So, what does this mean for us? The protostar phase is a reminder that even the mightiest stars begin humbly, as a faint glow in the darkness. It's a story of patience, persistence, and the incredible forces of nature working together to create something extraordinary. And as we peer into the depths of space, observing these young stars in their infancy, we're witnessing the very beginnings of light itself, a process that has shaped the universe since the dawn of time. Deep within the heart of a protostar, a monumental shift is about to occur. When the core temperature soars to around 10 million degrees Celsius, something extraordinary happens: nuclear fusion ignites. This isn't just a spark, it's the cosmic equivalent of flipping a switch, transforming a faint, glowing ember into a blazing star. At this critical moment, hydrogen atoms, the simplest and most abundant elements in the universe, collide with such force that they fuse together, creating helium. This process doesn't just produce a new element, it releases an astonishing amount of energy, the very energy that will power the star for billions of years. So, how does this fusion process work? Picture two hydrogen atoms hurtling toward each other at incredible speeds. Under normal conditions, their positive charges would repel each other, keeping them apart. But at the extreme temperatures and pressures found in the star's core, these atoms overcome that repulsion and merge. When they do, a tiny fraction of their mass is converted into pure energy, as described by Einstein's famous equation, E equals mc squared. It's this energy that radiates outward, creating the light and heat we associate with stars. But fusion isn't a one-time event, it's a continuous, self-sustaining reaction. Once ignited, the energy released by fusion creates pressure that pushes outward, counteracting the inward pull of gravity. This delicate balance between gravity and fusion keeps the star stable, preventing it from collapsing under its own weight or blowing itself apart. It's a cosmic dance, perfectly choreographed, that allows the star to shine steadily for millions or even billions of years. What's truly remarkable is the scale of this energy production. Even a single fusion reaction releases a tremendous amount of energy, and in a star's core, these reactions are happening countless times every second. To put it in perspective, the energy released by the sun's fusion reactions every second is equivalent to detonating billions of nuclear bombs simultaneously. And yet, this energy is released in a controlled, sustained manner, powering the star and, in the case of our sun, providing the energy necessary for life on Earth. Nuclear fusion doesn't just light up stars, it shapes the universe. The elements forged in stellar cores, like helium and eventually heavier elements, become the building blocks of planets, moons, and even life itself. Without fusion, the cosmos would be a dark, lifeless void. It's a process that bridges the gap between the microscopic world of atoms and the vast, luminous expanse of the universe. As we marvel at the stars above, it's worth remembering the incredible forces at work within them. Nuclear fusion is more than just a scientific phenomenon, it's the spark that lights the fire, the engine that drives the universe, and the reason we exist. And it all begins with a single, powerful collision deep within the heart of a star. Once nuclear fusion ignites in the core of a star, it enters what astronomers call the main sequence phase, the longest and most stable chapter of its life. This is the star's prime, where it shines steadily, fueled by the energy of fusion and held together by the delicate balance of forces at its core. Think of it like the star's golden years, a time of relative calm and consistency where it radiates light and heat into the cosmos. Our own sun, for instance, has been in this phase for roughly 4.6 billion years, and it's expected to remain there for billions more. But what exactly keeps a star stable during this phase? It all comes down to equilibrium, a cosmic tug of war between two opposing forces. On one side, gravity relentlessly pulls matter inward, compressing the star's core. On the other, the immense pressure generated by nuclear fusion pushes outward, resisting that collapse. This balance is so precise that even a small shift could dramatically alter the star's fate. It's a testament to the incredible harmony of the universe, where forces we can't see or touch work together to create something enduring and beautiful. Not all stars spend the same amount of time in the main sequence, though. The duration depends largely on the star's mass. Smaller stars, like red dwarfs, burn their fuel slowly and can remain in this phase for trillions of years, far longer than the current age of the universe. Larger stars, on the other hand, burn through their fuel at a much faster rate. A star 10 times more massive than the Sun, for example, might only stay in the main sequence for a few million years before moving on to the next stage of its life. During its time on the main sequence, a star transforms hydrogen into helium in its core, releasing energy that sustains its brilliance. But even this seemingly endless process has its limits. Over time, the star's core begins to run low on hydrogen, and the balance between gravity and fusion starts to shift. This marks the beginning of the end for the star's main sequence phase, setting the stage for the next chapter in its life cycle. What's fascinating is how much we can learn about a star's future by observing its behavior during this phase. By studying the light it emits, astronomers can determine its composition, temperature, and even how much fuel it has left. It's like reading the star's cosmic diary, revealing not just its past and present, but also hinting at what's to come. For us, the main sequence phase is a reminder of the incredible stability and resilience of stars. They aren't just static points of light in the sky, they're dynamic, evolving entities with their own life stories. And as we gaze up at the night sky, we're witnessing countless stars in their prime, each one a testament to the delicate balance that powers the universe. As we've seen, stars are born from the same basic ingredients, gas, dust, and gravity, but not all stars follow the same path. The key to understanding a star's destiny lies in one critical factor: its mass. Think of mass as a cosmic blueprint, determining everything from a star's brightness and color to its lifespan and ultimate fate. Whether a star will burn quietly for trillions of years or explode in a dazzling supernova depends on how much material it starts with. At one end of the spectrum are the low-mass stars, often referred to as red dwarfs. These stars are the cosmic marathon runners, burning their fuel at a slow, steady pace. Because they're so small, their cores don't reach the same extreme pressures as larger stars, which means their fusion reactions happen more gradually. This slow burn allows them to live incredibly long lives, trillions of years in some cases. To put that into perspective, the universe itself is only about 13.8 billion years old. So many red dwarfs we see today will still be shining long after our sun has faded. On the other end are the high-mass stars, the cosmic sprinters of the universe. These stars are born with a much larger supply of fuel, but they burn through it at a staggering rate. Their immense gravity creates extreme pressures and temperatures in their cores, driving fusion reactions that produce enormous amounts of energy. As a result, high-mass stars shine with incredible brightness, often appearing as blue or white in color. But this brilliance comes at a cost. Their lifespans are measured in mere millions of years, a blink of an eye compared to the slow-burning red dwarfs. What's truly fascinating is how these differences in mass shape the star's final acts. Low-mass stars like red dwarfs tend to fade quietly, cooling over time until they become dim, inert objects known as white dwarfs. High-mass stars, however, go out with a bang. When they exhaust their fuel, their cores collapse, triggering a catastrophic explosion called a supernova. These explosions are so powerful that they can outshine entire galaxies for a brief moment, scattering heavy elements like iron and gold into space elements that will one day form new stars, planets, and even life. The diversity of stellar masses doesn't just affect individual stars, it shapes the entire cosmos. Low-mass stars provide stability and longevity, while high-mass stars, despite their short lives, play a crucial role in enriching the universe with heavy elements. Without this variety, the universe would lack the complexity and diversity we see today. So, what can we learn from this interplay of mass and destiny? It's a reminder that even within the vastness of space, every star has a unique story to tell. Whether it's the quiet endurance of a red dwarf or the explosive finale of a supergiant, each star's journey is shaped by the forces of nature in ways that continue to captivate and inspire us. And as we study these celestial wonders, we gain not just a deeper understanding of the stars themselves, but also of the intricate processes that govern the universe. When we think of stars, we often picture them as solitary points of light scattered across the night sky. But the reality is far more intriguing. Most stars are born not alone, but in pairs or even larger groups. These stellar companions, known as binary star systems, are like cosmic dance partners, locked in an eternal gravitational embrace. Imagine two stars orbiting a shared center of mass, their paths intertwined in a delicate ballet that can last for billions of years. This isn't a rare phenomenon. Binary stars are incredibly common, making up a significant portion of the stars we observe in the universe. So how do these stellar duos come to be? The story begins, as it often does, in the depths of a molecular cloud. When a dense region of gas and dust collapses under gravity, it doesn't always form a single star. Instead, the cloud can fragment into multiple clumps, each one giving rise to its own star. If two of these clumps are close enough, their gravitational pull will bind them together, creating a binary system. It's like a cosmic coin toss. Sometimes nature decides to make one star, and other times it creates a pair. But binary stars aren't just two stars randomly orbiting each other. Their relationship is a complex interplay of gravity, motion, and energy. One star might be more massive than the other, influencing the system's dynamics in fascinating ways. For instance, the more massive star can exert a stronger gravitational pull, causing its smaller companion to orbit faster or follow a more elongated path. Over time, this interaction can lead to dramatic changes, such as one star transferring material to the other or even altering its shape. What's particularly captivating is the diversity of binary systems. Some pairs orbit so closely that their surfaces nearly touch, while others are separated by vast distances, taking centuries to complete a single orbit. In some cases, one star might outshine the other, making its companion nearly invisible to the naked eye. Yet, despite these differences, binary stars share a common trait. Their gravitational bond is unbreakable, a testament to the enduring forces that shape the cosmos. These systems also offer us a unique window into stellar evolution. By studying binary stars, astronomers can measure their masses, determine their ages, and even predict their ultimate fates. For example, if one star in a binary system explodes as a supernova, its companion might be flung into space, or the two could collapse into a pair of black holes, continuing their dance in a new, more dramatic form. The birth and life of binary stars remind us that the universe is full of partnerships, connections, and shared journeys. Whether they're locked in a tight embrace or orbiting each other from a distance, these stellar siblings tell a story of collaboration and balance, a story that's written in the stars themselves. And as we look up at the night sky, we're reminded that even in the vastness of space, nothing is truly alone. As we delve deeper into the cosmic dance of star formation, we encounter two unsung heroes, dust and gas. These seemingly humble ingredients are the very building blocks of stars, but their role goes far beyond just providing raw material. In the vast molecular clouds where stars are born, dust and gas work together in a delicate partnership, shaping the process in ways that might surprise you. Picture a cloud of gas, invisible and diffuse, drifting through space. Alone, it might never collapse into a star, but add dust grains, tiny particles no larger than a fraction of a millimeter, and the story changes dramatically. These grains act like cosmic catalysts, helping the gas cool and condense. How? By absorbing energy from the gas and then radiating it away as heat. dust allows the gas to lose energy and grow denser. It's like a cosmic air conditioner, gradually cooling the cloud until gravity can take over and pull it inward. But dust doesn't just cool the gas, it also provides a surface for chemical reactions to occur. On the surface of these grains, simple molecules like hydrogen can bond to form more complex compounds, including water and even organic molecules. This process, known as surface chemistry, is a crucial step in the journey from cloud to star. Without dust, these reactions would happen far more slowly, if at all, delaying or even preventing star formation. Once a star begins to form, dust and gas continue to play a vital role. The protostar is surrounded by a swirling disk of material, rich in both elements. Dust grains within this disk clump together, forming pebbles, rocks, and eventually planetesimals, the seeds of future planets. Meanwhile, the gas provides the pressure and energy needed to sustain the star's growth. Over time, much of this material is consumed by the star, but some remains, forming the building blocks of planets, moons, and even life. What happens to the leftover dust and gas? In some cases, it's swept away by the star's radiation, creating a glowing nebula that lights up the surrounding space. In others, it's incorporated into new stars, continuing the cycle of birth and renewal. This recycling of material is a hallmark of the universe, a reminder that nothing is ever truly lost, it's simply transformed. The interplay of dust and gas is a story of collaboration and transformation. Together, they create the conditions for star formation, shaping the birth of celestial bodies and the evolution of the cosmos. And as we peer into the depths of space, observing these processes in action, we gain a deeper appreciation for the intricate, interconnected nature of the universe. Dust and gas may seem insignificant on their own, but together they are the architects of light, life, and the very fabric of the cosmos. As a newborn star begins to shine, it doesn't just sit quietly in its cosmic cradle, it breathes. These breaths, known as stellar winds, are powerful streams of charged particles that surge outward from the star's surface, sweeping through its surroundings like a cosmic hurricane. Imagine a young star glowing with newfound energy, sending out gusts of wind so strong they can reshape the very fabric of space around it. These winds aren't just a byproduct of the star's formation. They're a crucial part of its story, shaping its environment and influencing its future. So, where do these stellar winds come from? It all starts with the star's intense radiation and magnetic fields. As the star heats up, its outer layers become charged with energy, creating a high-pressure environment. This pressure builds until it overcomes the star's gravity, launching particles into space at incredible speeds. These particles, mostly protons and electrons, race outward, carrying with them the star's energy and momentum. It's a process that's both violent and beautiful, a reminder of the raw power hidden within even the youngest stars. But stellar winds don't just blow aimlessly, they have a profound impact on the star's surroundings. As they surge outward, they collide with the gas and dust left over from the star's birth, carving out vast cavities in the molecular cloud. These cavities, often glowing with the light of the star itself, become a kind of cosmic clearing, a space where the star can shine without obstruction. At the same time, the winds push away nearby material, preventing it from collapsing and forming new stars. In this way, stellar winds act as both sculptors and gatekeepers, shaping the star's environment while limiting the growth of its neighbors. The effects of stellar winds aren't limited to the immediate area around the star. Over time, these winds can travel vast distances, influencing the structure of entire galaxies. In some cases, they can even trigger the formation of new stars by compressing gas and dust in their path, creating pockets of density that eventually collapse under gravity. It's a fascinating paradox. Stellar winds can prevent star formation in one region while setting the stage for it in another, a reminder of the complex and interconnected nature of the cosmos. What's truly remarkable is how these winds evolve as the star grows. In the early stages, they're fierce and chaotic, driven by the star's intense energy and rapid rotation. But as the star settles into its main sequence phase, the winds often become more stable, flowing outward in a steady stream. This evolution mirrors the star's own journey, from a turbulent youth to a mature, steady presence in the galaxy. Stellar winds are more than just a cosmic phenomenon. They're a testament to the dynamic forces at work in the universe. They remind us that even the smallest actions, like the breath of a newborn star, can have far-reaching consequences, shaping the cosmos in ways we're only beginning to understand. And as we study these winds, we gain not just insight into the lives of stars, but also a deeper appreciation for the intricate web of interactions that define our universe. In the grand tapestry of star formation, there's an invisible force at work, one that shapes the birth of stars in ways we're only beginning to understand. These are magnetic fields, the unseen threads that weave through the cosmos, guiding the collapse of gas and dust into the fiery hearts of newborn stars. While gravity might be the dominant force pulling the material together, magnetic fields act like cosmic conductors, orchestrating the flow of matter and energy with precision. So, how do these magnetic fields form? It all begins with charged particles, electrons and protons moving through space. As these particles spiral and swirl, they generate electric currents, which in turn create magnetic fields. Over time, these fields can become incredibly strong, especially within the dense regions of molecular clouds. Picture these fields as invisible lines of force, stretching across vast distances, connecting the tiniest particles to the largest structures in the universe. But magnetic fields don't just sit idly by, they actively shape the process of star formation. As a molecular cloud begins to collapse, the magnetic fields within it can channel the flow of gas and dust, directing material into specific regions. This creates a kind of cosmic scaffolding, guiding the formation of dense clumps that will eventually become protostars. Without these fields, the collapse of a cloud might be chaotic and disorganized, but with them, the process becomes more structured and efficient. One fascinating aspect of magnetic fields is their ability to resist gravity, at least to a point. As gravity pulls material inward, the magnetic fields push back, creating a delicate balance. This resistance can slow down the collapse of a cloud, giving it time to fragment into multiple clumps, each one destined to become a star. In this way, magnetic fields play a crucial role in determining how many stars form within a single molecular cloud. As the protostar takes shape, magnetic fields continue to influence its development. They can shape the swirling disk of material around the young star, creating jets of gas that shoot out from its poles. These jets, often visible as glowing streams of light, are a direct result of the interplay between magnetic fields and the star's rotation. They help to carry away excess angular momentum, allowing the star to grow and stabilize. Yet, despite their importance, magnetic fields remain one of the most challenging aspects of star formation to study. They're invisible to the naked eye and require sophisticated instruments to detect. But through careful observation and advanced simulations, astronomers are uncovering the vital role these fields play in shaping the cosmos. The story of magnetic fields is a reminder that the universe is full of unseen forces, quietly shaping the birth and evolution of stars. They're the hidden architects of the cosmos, guiding the flow of matter and energy in ways that continue to inspire and mystify us. And as we peer deeper into the mysteries of star formation, we're reminded that even the forces we can't see are essential to the beauty and complexity of the universe. Among the countless stars that light up the night sky, a select few stand out not just for their brilliance but for their sheer size and power. These are the massive stars, the giants among giants, born with more than 8 times the mass of our Sun. Though rare, their impact on the universe is profound. They burn brighter, live faster, and die more explosively than most stars, leaving behind a legacy that shapes the cosmos itself. But how do these colossal stars come to be, and what makes their lives so different from their smaller counterparts? The story of massive stars begins like any other, within the swirling depths of a molecular cloud. But while smaller stars form from modest clumps of gas and dust, massive stars require something extraordinary, a colossal reservoir of material. Imagine a molecular cloud not as a gentle, drifting mist, but as a turbulent, chaotic storm. Within this storm, dense regions of gas and dust collapse under gravity, pulling in vast amounts of material. For a massive star to form, this process must happen on an enormous scale, with enough material to create a star that's not just big, but truly immense. Yet, forming a massive star isn't as simple as gathering more gas and dust. These stars face unique challenges from the very beginning. One of the most significant is radiation pressure. As a massive protostar begins to take shape, it heats up rapidly, emitting intense radiation. This radiation pushes outward, resisting the inward pull of gravity. In smaller stars, gravity easily overcomes this pressure, but for massive stars, the balance is far more delicate. The radiation can blow away surrounding material, starving the star of the fuel it needs to grow. It's a cosmic tug-of-war where the star must fight to gather enough mass before its own radiation drives its potential building blocks away. Despite these challenges, massive stars do form, and when they do, they shine with unparalleled brilliance. Their cores reach staggering temperatures and pressures, driving nuclear fusion at a furious rate. While a star like our Sun fuses hydrogen into helium over billions of years, a massive star burns through its fuel in just a few million. This rapid consumption gives them their dazzling luminosity, but it also shortens their lifespans dramatically. And then there's the matter of their explosive deaths. When a massive star exhausts its fuel, it doesn't fade quietly, it goes out in a blaze of glory. The core collapses, triggering a supernova that can outshine an entire galaxy. In these cataclysmic explosions, heavy elements like iron, gold, and uranium are forged and scattered across the universe. These elements become the building blocks of new stars, planets, and even life itself. Without massive stars, the universe would lack the diversity and complexity we see today. The birth and life of massive stars are a testament to the extremes of nature. They remind us that even in the vastness of space, there are forces at work that push the boundaries of what's possible. And as we study these cosmic giants, we gain not just a deeper understanding of the stars themselves, but also of the intricate processes that shape the universe. From their turbulent beginnings to their explosive ends, massive stars are more than just celestial wonders, they're the architects of the cosmos. When a massive star reaches the end of its life, it doesn't merely fade away, it leaves the universe with a final, spectacular gift. This gift comes in the form of a supernova, one of the most powerful and awe-inspiring events in the cosmos. A supernova is more than just a dazzling explosion. It's a cosmic crucible, forging and scattering the heavy elements that make up everything from the planets beneath our feet to the air we breathe. Without these cataclysmic events, the universe as we know it, rich, diverse, and teeming with life, wouldn't exist. So, what exactly happens during a supernova? In the final moments of a massive star's life, its core collapses under its own gravity, triggering an explosion so immense it can outshine entire galaxies. This explosion releases an extraordinary amount of energy, blasting the star's outer layers into space at incredible speeds. Within those layers are elements forged in the star's core, elements like carbon, oxygen, silicon, and even gold. These materials, once locked deep within the star, are now set free, dispersing into the surrounding cosmos like seeds scattered by a cosmic wind. But the story doesn't end there. The shockwaves from a supernova ripple through nearby molecular clouds, compressing the gas and dust within them. This compression can trigger the collapse of these clouds, igniting the birth of new stars. It's a beautiful cycle. One star's death becomes the catalyst for another's birth. In this way, supernovae act as cosmic fertilizers, enriching the universe with the raw materials needed for star formation and ultimately for life itself. What's truly remarkable is the scale of this process. A single supernova can release enough energy to outshine an entire galaxy for weeks, and the heavy elements it produces can travel vast distances, seeding new star systems far from their origin. Over billions of years, these elements accumulate, forming the building blocks of planets, moons, and even the complex molecules that make life possible. Every atom of oxygen in your lungs, every speck of iron in your blood, these were forged in the hearts of stars and scattered by supernova long before Earth even existed. Supernova also serve as cosmic laboratories, offering us a glimpse into the extreme conditions of the universe. By studying these explosions, astronomers can learn about the physics of stellar death, the creation of heavy elements, and the forces that shape galaxies. Each supernova is a fleeting moment of brilliance, but its legacy endures, shaping the cosmos for generations to come. The role of supernova in the universe is a testament to the interconnectedness of all things. From the death of a single star comes the birth of countless others, each one carrying the potential for new worlds and new life. And as we look up at the night sky, we're reminded that even in destruction, there is creation, a cycle as old as the universe itself and as beautiful as the stars that light our way. In the vast expanse of the universe, stars rarely form in isolation. Instead, they often come into existence as part of larger family star clusters, bustling communities where hundreds or even thousands of stars are born together from the same molecular cloud. These clusters are like cosmic neighborhoods, places where stars grow up side by side, shaping each other's destinies through their gravitational interactions. But what brings these stars together in the first place, and what happens to these celestial communities as time goes on? The story of star clusters begins in the heart of a massive molecular cloud. When such a cloud collapses under gravity, it doesn't always form a single star. Instead, the cloud fragments into multiple dense regions, each one giving rise to its own star. Because these regions are often close together, the stars they produce remain bound by gravity, creating a cluster. It's like a cosmic nursery where stars are born in close proximity, sharing the same origins and the same raw materials. What makes star clusters so fascinating is the way their members interact. In these crowded environments, stars aren't just neighbors, they're constantly influencing one another. Their gravitational pull can alter each other's orbits, while their radiation and stellar winds can shape the surrounding gas and dust. In some cases, stars may even collide or merge, creating new, more massive stars. It's a dynamic and ever-changing environment where the actions of one star can ripple through the entire cluster, but not all star clusters are the same. There are two main types, open clusters and globular clusters. Open clusters are relatively young, containing anywhere from a few dozen to a few thousand stars. They are often found in the spiral arms of galaxies where star formation is still active. These clusters are loosely bound, and over time, their stars may drift apart, scattering into the wider galaxy. Globular clusters, on the other hand, are much older and more tightly packed. They can contain hundreds of thousands of stars, all bound together by gravity in a dense, spherical shape. These clusters are ancient relics often found in the outskirts of galaxies. Their stars are some of the oldest in the universe, offering a glimpse into the early stages of galactic evolution. Over time, star clusters evolve in fascinating ways. Some may dissolve entirely, their stars dispersing into the galaxy as individuals. Others may remain intact for billions of years, their stars growing old together. In some cases, clusters may even collide with one another, merging to form even larger communities. These interactions leave behind a rich tapestry of stellar history, a record of the forces that shape the cosmos. Star clusters are more than just collections of stars. They're living, breathing communities, each with its own story to tell. They remind us that even in the vastness of space, stars are rarely alone. And as we study these cosmic neighborhoods, we gain a deeper understanding of the social lives of stars, the forces that shape their evolution, and the interconnected nature of the universe itself. Whether they're young, open clusters or ancient globulars, these celestial communities are a testament to the beauty and complexity of the cosmos. Imagine a universe where the stars and galaxies we see are just the tip of the iceberg. A vast, hidden framework exists, shaping everything from the largest cosmic structures to the birth of individual stars. This invisible force is dark matter, a mysterious substance that makes up roughly 85% of the universe's mass. Unlike the stars and planets we can observe, dark matter doesn't emit, absorb, or reflect light. It's completely invisible, yet its gravitational influence is everywhere, weaving an unseen web that holds the cosmos together. So, how does dark matter affect the birth of stars? To understand its role, we need to think beyond the visible. When a molecular cloud begins to collapse under gravity, it's not just the gas and dust at work. Dark matter is also pulling from the shadows. Its gravitational presence amplifies the collapse, helping to gather material into denser clumps. Without dark matter, the process of star formation would be far slower and less efficient. It's like having an invisible hand guiding the flow of cosmic ingredients, ensuring everything comes together at just the right time and place. But dark matter's influence doesn't stop there. On a larger scale, it shapes the very structure of the universe. Galaxies are embedded in massive halos of dark matter, which act as cosmic scaffolding. These halos provide the gravitational framework that allows galaxies to form and evolve. Without dark matter, galaxies as we know them might never have come into existence. It's a humbling thought that something we can't see or directly detect is so fundamental to the universe's architecture. One of the most intriguing mysteries of dark matter is its interaction, or lack thereof, with light and ordinary matter. While it exerts a gravitational pull, it doesn't collide with particles in the way we'd expect. This makes it incredibly difficult to study. Scientists have devised ingenious ways to detect its presence indirectly, such as observing the bending of light around massive objects, a phenomenon known as gravitational lensing. Yet, despite decades of research, dark matter remains one of the greatest puzzles in modern astrophysics. What's truly fascinating is how dark matter's influence extends to the smallest scales of star formation. In regions where molecular clouds collapse, dark matter's gravitational pull can create the initial conditions needed for stars to ignite. It's a reminder that even the birth of a single star is part of a much larger cosmic dance, choreographed by forces we're still striving to understand. The role of dark matter in star formation is a testament to the hidden complexity of the universe. It challenges us to look beyond what we can see, to explore the unseen forces that shape our reality. And as we continue to unravel its mysteries, we're reminded that the cosmos is far more intricate and interconnected than we ever imagined. From the tiniest spark of a newborn star to the vast structure of galaxies, dark matter is the silent partner guiding the universe's grand design. As a star ignites and begins to shine, it doesn't just light up the cosmos, it also sets the stage for the creation of worlds. Surrounding many newborn stars is a swirling disk of leftover gas and dust, a cosmic byproduct of the star's formation. This disk, known as a protoplanetary disk, is more than just debris. It's the birthplace of planets. Within this chaotic, spinning environment, tiny particles collide, stick together, and gradually grow into the building blocks of worlds. It's here, in these disks, that the story of planetary systems begins. But how does a cloud of dust and gas transform into planets? The process starts with the smallest grains of dust, no larger than specks of sand. These grains clump together, forming pebbles, then rocks, and eventually boulders. Over thousands of years, these boulders grow into planetesimals, chunks of material large enough to exert their own gravitational pull. Once this milestone is reached, the planetesimals begin to attract more material, growing larger and larger until they become protoplanets. It's a slow, incremental process, but over millions of years, these protoplanets can evolve into fully fledged planets, complete with atmospheres, oceans, and even the potential for life. The star at the center of this process plays a crucial role in shaping its planetary family. Its gravity holds the disk together, while its radiation and stellar winds influence the distribution of material. For example, the inner regions of the disk closer to the star tend to be hotter and denser, favoring the formation of rocky planets like Earth. Farther out, where temperatures are cooler, gas giants like Jupiter and Saturn can take shape, their massive atmospheres capturing the lighter elements that dominate the outer disk. What's truly remarkable is the diversity of planetary systems that can emerge from these disks. Some stars host compact systems with tightly packed planets, while others have sprawling arrangements with worlds orbiting at great distances. In some cases, planets may even migrate from their original locations, moving closer to or farther from their star over time. This migration can lead to dramatic changes in a system structure, shaping the orbits and interactions of its planets. The formation of planetary systems is more than just a scientific curiosity. It's the story of how worlds like our own come to be. Every planet, moon, and asteroid in our solar system owes its existence to the swirling disk that once surrounded our young sun. And as we discover more exoplanets orbiting distant stars, we're reminded that this process is happening throughout the galaxy, creating countless worlds with their own unique histories and possibilities. The connection between stars and their planetary offspring is a testament to the enduring creativity of the universe. From the tiniest grains of dust to the vast, complex systems they become, planets are more than just celestial bodies. They're the legacy of the stars that gave them life. And as we explore these systems, we gain not just a deeper understanding of the cosmos, but also a greater appreciation for the delicate, beautiful processes that shape our existence. From the moment a star begins to shine, it doesn't just illuminate the cosmos, it transforms it. One of the most powerful tools in a young star's arsenal is radiation, the energy it emits in the form of light, heat, and other electromagnetic waves. This radiation doesn't just announce the star's presence, it actively shapes the environment around it, carving out its place in the universe. But how does this process work? And what does it mean for the birth of other stars nearby? When a star first ignites, its radiation floods the surrounding molecular cloud, ionizing the gas and dust. Ionization occurs when the star's intense light strips electrons from atoms, creating charged particles that glow in vibrant colors. This is what gives us the stunning nebulae we see in images from telescopes. Cosmic clouds lit up like neon signs, painted with hues of red, blue, and green. These glowing remnants of stellar nurseries aren't just beautiful, they're also a record of the star's early influence on its surroundings. But radiation doesn't just create glowing nebulae, it also heats the gas and dust in the cloud, raising its temperature and pressure. This heating can have a profound effect on the star-forming process. In some cases, it can prevent nearby gas from collapsing, effectively putting a pause on the birth of new stars. It's like a cosmic stop sign, signaling that the area is no longer suitable for star formation. This phenomenon, known as feedback, ensures that stars don't form too close to one another, spacing them out across the galaxy. On the other hand, radiation can also trigger star formation in unexpected ways. The shock waves and pressure changes it creates can compress distant regions of the cloud, pushing them to collapse and ignite new stars. It's a delicate balance. Radiation can both suppress and stimulate star formation, depending on the conditions. This dual role makes radiation one of the most dynamic forces in the cosmos, a force that shapes not just individual stars but entire stellar neighborhoods. The glowing nebulae left behind by young stars also serve as cosmic laboratories, offering astronomers a window into the early stages of star formation. By studying the light emitted by these regions, scientists can learn about the composition, temperature, and density of the gas and dust within them. This information helps us piece together the story of how stars are born, how they influence their surroundings, and how they shape the evolution of galaxies. Radiation's role in star formation is a reminder that every star is an active participant in the cosmos, not just a passive observer. From the moment it ignites, a star begins to sculpt its environment, creating a legacy that lasts long after its light fades. And as we gaze at the glowing nebulae scattered across the night sky, we're witnessing the ongoing story of stellar birth, a story shaped by the invisible hand of radiation, the force that lights the universe and guides its evolution. In the vast spectrum of celestial objects, there exists a category that defies easy classification: brown dwarfs. These enigmatic bodies are neither fully stars nor ordinary planets, but something in between. Too massive to be considered planets, yet not massive enough to ignite the sustained nuclear fusion that defines a true star, brown dwarfs occupy a unique and fascinating niche in the cosmos. Often referred to as failed stars, they are anything but failures. Instead, they are hidden gems, offering us a rare glimpse into the fine line that separates stars from planets. So, how do brown dwarfs come to be? Their formation begins much like that of a star, within the dense, swirling clouds of gas and dust that populate molecular clouds. As gravity pulls material together, a protostar begins to take shape. But for a brown dwarf, something critical is missing: mass. While a typical star gathers enough material to reach at least 8% of the sun's mass, enough to ignite hydrogen fusion, a brown dwarf falls short, topping out at around 7.5%. Without the necessary mass to sustain fusion, the object cools and dims, settling into its identity as a brown dwarf. What makes brown dwarfs so intriguing is their ability to bridge two worlds. In their early stages, they resemble stars, glowing faintly as they radiate heat from their gravitational collapse. Over time, however, they cool and fade, becoming more planet-like. Some brown dwarfs even host their own systems of planets or moons, blurring the line between star and planet even further. But brown dwarfs aren't just curiosities, they hold valuable clues about the process of star formation. By studying them, astronomers can explore the lower limits of stellar mass, answering questions like: how small can a star be? What conditions are necessary for nuclear fusion to ignite? And what happens when those conditions aren't met? Brown dwarfs serve as cosmic test cases, helping us understand the boundaries that define stars and planets alike. One of the most fascinating aspects of brown dwarfs is their diversity. Some are relatively warm, radiating heat from their recent formation, while others are so cold they resemble gas giants like Jupiter. In fact, the coldest brown dwarfs discovered to date have temperatures comparable to a chilly Earth day, making them nearly indistinguishable from planets. This wide range of temperatures and characteristics makes brown dwarfs a rich field of study, offering insights into both stellar and planetary science. Despite their name, brown dwarfs are far from dull. They challenge our understanding of what it means to be a star or a planet, pushing us to rethink the categories we use to describe the universe. And as we continue to discover more of these hidden gems, we're reminded that the cosmos is full of surprises waiting to be uncovered. Brown dwarfs may not light up the sky like their stellar cousins, but they shine brightly in their own unique way, offering a window into the mysteries of the universe. In the cosmic dance of star formation, turbulence is the wild card, a force that stirs the pot, creating the chaotic, swirling motions that set the stage for stellar birth. Picture a molecular cloud not as a calm, serene expanse, but as a churning, stormy sea. Within this turbulent environment, gas and dust are whipped into frenzied motion, colliding and compressing in ways that can spark the creation of stars. It's a dynamic, ever-changing landscape where the forces of chaos and order work hand in hand to shape the cosmos. So, what exactly is turbulence and how does it influence star formation? At its core, turbulence is the random, swirling motion of gas within a molecular cloud. These motions can be caused by a variety of factors, from the shockwaves of nearby supernova to the gravitational pull of passing stars. As the gas swirls and eddies, it creates regions of higher density where the material is compressed enough to trigger collapse under gravity. Think of it like a cosmic pressure cooker. Turbulence stirs the ingredients, creating the right conditions for stars to ignite. But turbulence doesn't just compress gas and dust, it also plays a crucial role in shaping the structure of molecular clouds. Without turbulence, these clouds might remain diffuse and static, never reaching the densities needed for star formation. Turbulence breaks the cloud into smaller, denser clumps, each one a potential site for stellar birth. It's like a sculptor working with clay, shaping the cloud into a mosaic of dense cores and wispy filaments. One of the most fascinating aspects of turbulence is its ability to influence the size and distribution of stars within a cloud. In highly turbulent regions, the chaotic motions can lead to the formation of multiple stars, often in close proximity. This creates star clusters, bustling communities where stars grow up together, shaping each other's destinies through their gravitational interactions. In less turbulent regions, stars may form in isolation, scattered across the cloud like cosmic loners. Turbulence also helps to regulate the pace of star formation. In some cases, it can accelerate the process, compressing gas and dust quickly and igniting stars in rapid succession. In others, it can slow things down, creating a more gradual, steady pace of stellar birth. This delicate balance between chaos and order is what makes turbulence such a powerful and unpredictable force in the cosmos. As we explore the role of turbulence in star formation, we're reminded that the universe is far from static. It's a dynamic, ever-changing place where even the most chaotic forces play a vital role in shaping the cosmos. From the swirling motions of molecular clouds to the birth of stars, turbulence is the unseen hand that stirs the pot, creating the conditions for light and life to emerge. And as we study these chaotic forces, we gain a deeper appreciation for the intricate, beautiful processes that drive the evolution of the universe. When a massive star reaches the end of its life, it doesn't just fade away, it leaves behind a legacy so extraordinary it defies imagination. These remnants, known as neutron stars, are among the most bizarre and fascinating objects in the universe. Imagine taking the mass of a star, something that could be millions of times larger than Earth, and squishing it down into a sphere no bigger than a city. The result is an object so dense that a single teaspoon of its material would weigh billions of tons. Neutron stars are the cosmic equivalent of a diamond forged in the crucible of a supernova explosion, a dazzling, dense remnant of stellar death. But how do these incredible objects come to be? The story begins with the death of a massive star. When such a star exhausts its nuclear fuel, its core can no longer support the crushing weight of its outer layers. Gravity takes over, compressing the core to unimaginable densities. In a matter of seconds, the core collapses, triggering a supernova explosion that blasts the star's outer layers into space. What remains is the core itself, an ultra-dense neutron star. The physics behind this process is as mind-bending as the result. As the core collapses, protons and electrons are forced together, merging to form neutrons. These neutrons are packed so tightly that the core becomes a single, city-sized neutron-rich sphere. It's a state of matter unlike anything we encounter on Earth, where the forces at play are so extreme they challenge our understanding of physics. Neutron stars aren't just curiosities, they're cosmic laboratories, offering insights into the behavior of matter under extreme conditions. For example, their intense gravitational fields can bend light and distort space-time, creating effects predicted by Einstein's theory of general relativity. Some neutron stars, known as pulsars, emit beams of radiation that sweep across the sky like cosmic lighthouses, allowing astronomers to study their properties in incredible detail. But perhaps the most fascinating aspect of neutron stars is what they reveal about the life and death of stars. Their formation marks the end of a massive star's journey, but it's also the beginning of a new chapter in the cosmic story. The heavy elements forged in the supernova explosion are scattered into space, seeding the next generation of stars and planets. In this way, neutron stars are more than just remnants, they're the architects of the future, shaping the evolution of the universe. The birth of a neutron star is a testament to the incredible forces at work in the cosmos. It's a reminder that even in death, stars can create something extraordinary, something that continues to shape the universe long after their light has faded. And as we study these dense, mysterious objects, we gain not just a deeper understanding of stellar death, but also a greater appreciation for the intricate, beautiful processes that drive the evolution of the cosmos. At the heart of every galaxy lies one of the universe's most enigmatic and powerful forces, the black hole. These cosmic behemoths are regions of space where gravity is so intense that nothing, not even light, can escape their pull. They are the ultimate cosmic mystery, born from the remnants of massive stars or the collapse of unimaginably dense gas clouds. But black holes aren't just destructive forces. They play a surprisingly active role in shaping the cosmos, influencing everything from star formation to the evolution of entire galaxies. So, how do these invisible giants leave their mark on the universe? Let's start with their origins. Most black holes form when massive stars reach the end of their lives. After exhausting their nuclear fuel, these stars collapse under their own gravity, triggering a supernova explosion. What remains is a core so dense that it warps space and time, creating a black hole. But black holes can also form through other processes, such as the direct collapse of massive gas clouds in the early universe. Regardless of how they come to be, their presence is impossible to ignore. One of the most fascinating ways black holes influence star formation is through their immense gravitational pull. In the chaotic environment of a galaxy's center, a supermassive black hole can dominate the surrounding region, pulling in gas and dust from its surroundings. As this material spirals inward, it forms an accretion disk, a swirling, superheated ring of matter that orbits the black hole. The friction and heat within this disk can generate enormous amounts of energy, creating some of the brightest objects in the universe, known as quasars. But the story doesn't end there. The energy and shockwaves produced by the black hole's activity can have a profound effect on its galactic neighborhood. In some cases, this energy can compress nearby gas clouds, triggering the formation of new stars. It's a cosmic paradox. A black hole, often thought of as a devourer of light, can actually help ignite the birth of stars. On the other hand, black holes can also suppress star formation. The intense radiation and powerful jets of particles they emit can heat up surrounding gas, preventing it from cooling and collapsing into stars. This delicate balance between creation and destruction is one of the key ways black holes shape the evolution of galaxies. Beyond their influence on star formation, black holes play a crucial role in the structure of galaxies themselves. Supermassive black holes, which reside at the center of most galaxies, help regulate the growth and stability of their host galaxies. Their gravitational pull can anchor entire galactic systems, while their energy output can influence the distribution of stars and gas over vast distances. The study of black holes is a journey into the extremes of physics and the unknown. They challenge our understanding of gravity, space, and time, offering glimpses into the fundamental laws that govern the universe. And as we continue to explore their mysteries, we're reminded that even the darkest corners of the cosmos hold the keys to understanding the grand tapestry of creation. From their role in star formation to their influence on galaxies, black holes are not just cosmic anomalies, they are the architects of the universe's most profound and beautiful processes. While massive stars go out with a bang, their smaller counterparts meet a quieter, more serene fate. Low-mass stars like our Sun don't explode in supernova or collapse into black holes. Instead, they end their lives as white dwarfs, dense, Earth-sized remnants that glow faintly as they cool over billions of years. These cosmic embers are the final chapter in the story of most stars, a gentle conclusion to a stellar life that once burned brightly. But how do these remarkable objects come to be, and what can they tell us about the ultimate fate of stars like our own? The journey to becoming a white dwarf begins when a low-mass star exhausts its nuclear fuel. After billions of years of fusing hydrogen into helium, the star reaches a point where it can no longer sustain fusion in its core. As the core's energy production dwindles, the outer layers of the star expand, transforming it into a red giant. This bloated phase is both beautiful and destructive, as the star swells to hundreds of times its original size, engulfing any nearby planets in its path. But the red giant phase doesn't last forever. Eventually, the star sheds its outer layers, creating a glowing shell of gas and dust known as a planetary nebula. At the center of this nebula lies the star's exposed core, now a white dwarf. This core is incredibly dense, packing the mass of a star into a volume no larger than Earth. A single teaspoon of white dwarf material would weigh several tons, a testament to the extreme conditions within. What's fascinating about white dwarfs is how they defy our everyday understanding of matter. Under the immense pressure of their own gravity, the electrons within them are crushed so tightly that they form a state known as degenerate matter. This exotic material is what prevents the white dwarf from collapsing further, providing the stability it needs to endure for billions of years. Over time, white dwarfs gradually cool and fade, transitioning from a brilliant white to a dim red, and eventually to a cold, dark object known as a black dwarf. However, the universe isn't old enough for any black dwarfs to exist, yet the cooling process takes far longer than the current age of the cosmos. White dwarfs aren't just remnants of stellar life, they're also cosmic time capsules. By studying their composition, astronomers can learn about the star that created them, including its history and the elements it forged during its lifetime. Some white dwarfs even host planetary systems, offering clues about the fate of planets that survived their star's red giant phase. The story of white dwarfs is a reminder that not all stellar deaths are dramatic. For most stars, the end is a quiet, graceful fade into the cosmic background. And as we study these faint, enduring objects, we gain a deeper understanding of the life cycles of stars and the intricate processes that shape the universe. From their formation to their slow cooling, white dwarfs are a testament to the enduring beauty and complexity of the cosmos. At the heart of nearly every galaxy, including our own Milky Way, lies a cosmic titan, a supermassive black hole. These immense objects, millions or even billions of times more massive than the Sun, are more than just gravitational vacuums. They are galactic architects shaping the formation of stars and the very structure of the galaxies they inhabit. But how do these invisible giants, hidden at the centers of galaxies, exert such profound influence over the cosmos? One of the most striking ways supermassive black holes impact their surroundings is through their gravitational pull. Imagine a whirlpool at the center of a vast ocean, drawing everything toward it. The black hole's gravity is so immense that it can pull in gas, dust, and even entire stars, creating a swirling disk of superheated material known as an accretion disk. This disk doesn't just orbit the black hole, it radiates tremendous energy, often outshining all the stars in the galaxy combined. In some cases, this energy manifests as quasars, the brightest objects in the universe, visible from billions of light years away. But the influence of supermassive black holes goes far beyond their immediate surroundings. The energy they release through radiation, jets of particles, and shockwaves can travel vast distances, reaching the farthest corners of their host galaxies. This energy can have a dual effect on star formation. On one hand, it can compress gas clouds, triggering the collapse of material and igniting the birth of new stars. It's like a cosmic spark lighting the fuse for stellar creation. On the other hand, the intense heat and pressure generated by the black hole's activity can also prevent gas from cooling and collapsing, effectively putting a halt to star formation in certain regions. This delicate balance between creation and destruction is one of the key ways supermassive black holes shape their galaxies. In some galaxies, the black hole's influence leads to bursts of star formation, creating dense clusters of young, bright stars. In others, it can suppress star formation entirely, leaving vast regions of the galaxy quiet and dark. The interplay between these forces is what gives each galaxy its unique structure and character, from spiral arms filled with young stars to elliptical galaxies dominated by ancient, dim ones. Supermassive black holes also play a crucial role in the evolution of galaxies over cosmic time. Their growth is closely tied to the growth of their host galaxies, a relationship known as coevolution. As a galaxy grows, so does its central black hole, feeding on the gas and stars drawn into its grasp. This process isn't one-sided. The black hole's energy output can regulate the galaxy's growth, creating a feedback loop that shapes its destiny. In this way, supermassive black holes are not just passive inhabitants of galaxies, they are active participants in their evolution. The story of supermassive black holes is a testament to the interconnectedness of the universe. From the tiniest particles swirling in their accretion disks to the vast structures of galaxies, these cosmic giants shape the cosmos in ways we're only beginning to understand. And as we study their influence, we gain not just insight into the life cycles of galaxies, but also a deeper appreciation for the forces that drive the universe's grand design. Whether they are igniting the birth of stars or shaping the fate of entire galaxies, supermassive black holes are the unseen architects of the cosmos, weaving the fabric of the universe itself. Beyond the familiar planets of our solar system lies a universe teeming with worlds we're only beginning to discover: exoplanets. These distant planets, orbiting stars far beyond our sun, are more than just points of light in the night sky. They are windows into the incredible diversity of star formation, offering clues about how stars and their planetary systems come to be. From scorching hot gas giants to icy, Earth-like worlds, exoplanets come in a staggering variety of forms, each one a unique product of its stellar environment. But what exactly leads to the birth of these distant worlds, and what can they teach us about the stars that form them? The story of exoplanets begins in the same swirling disks of gas and dust that give rise to stars. When a star is born, it's often surrounded by a protoplanetary disk, a flat, rotating ring of leftover material. Within this disk, tiny particles of dust collide and stick together, gradually growing into pebbles, rocks, and eventually planetesimals. Over time, these planetesimals merge to form protoplanets, which can grow into full-fledged planets through further collisions and accretion. It's a process that mirrors the formation of our own solar system, but with countless variations depending on the star's size, composition, and environment. One of the most fascinating aspects of exoplanet formation is the sheer diversity it produces. Some stars host compact systems with tightly packed planets, while others have sprawling arrangements where worlds orbit at great distances. Gas giants like Jupiter and Saturn often form in the cooler outer regions of the disk, where they can capture lighter elements like hydrogen and helium. Rocky planets like Earth tend to form closer to the star, where temperatures are high enough to melt ice and vaporize volatile compounds, leaving behind heavier elements like iron and silicon. But exoplanets aren't just passive byproducts of star formation, they actively shape their environments. As they grow, they interact with the disk, carving gaps and creating spiral patterns that can influence the formation of other planets. In some cases, planets may migrate from their original orbits, moving closer to or farther from their star over time. This migration can lead to dramatic changes in a system's structure, creating the varied and dynamic arrangements we observe today. What makes exoplanets so valuable to astronomers is the insight they provide into the conditions of their birth. By studying their sizes, compositions, and orbits, we can piece together the history of their formation and the environments that shaped them. For example, the discovery of hot Jupiter's gas giants orbiting extremely close to their stars challenged our understanding of planet formation, showing that migration can play a key role in shaping planetary systems. Similarly, the detection of Earth-like planets in the habitable zone, where liquid water could exist, raises tantalizing questions about the potential for life beyond our solar system. Exoplanets also offer a unique perspective on the stars they orbit. The composition and behavior of a star can have a profound impact on its planets, from the intensity of its radiation to the stability of its orbit. In turn, planets can influence their stars, creating subtle gravitational tugs or even triggering stellar activity. This interplay between stars and their planetary systems is a reminder of the interconnectedness of the cosmos, where every object is shaped by the forces around it. The study of exoplanets is more than just a scientific endeavor. It's a journey into the unknown, a quest to understand the vast and varied worlds that populate our galaxy. And as we discover more of these distant planets, we're reminded that the universe is full of surprises, each one offering a new piece of the puzzle. From the birth of stars to the formation of planets, the story of exoplanets is a testament to the creativity and complexity of the cosmos, a story that continues to unfold with every new discovery. Amid the swirling chaos of molecular clouds and the birth of stars, there's another player in the cosmic drama, one that's invisible yet immensely powerful. These are cosmic rays, high-energy particles racing through space at nearly the speed of light. Born from supernova, black holes, and other extreme cosmic events, these particles are more than just space travelers. They're energetic messengers, carrying secrets about the universe and playing a surprising role in the birth of stars and planets. So, what exactly are cosmic rays? Imagine tiny particles, protons, electrons, and even atomic nuclei hurtling through the void, energized to levels far beyond anything we can create on Earth. When these particles collide with gas in molecular clouds, they can ionize atoms, stripping away electrons and leaving behind charged particles. This ionization process isn't just a side effect, it's a catalyst for star formation. By ionizing gas, cosmic rays lower its temperature and increase its density, making it easier for gravity to pull the material together and ignite the birth of a star. But cosmic rays don't just help stars form, they also shape the environments where stars are born. In regions of molecular clouds where cosmic rays are abundant, their energy can create turbulence, stirring up gas and dust and creating the conditions needed for star formation. It's like a cosmic whirlwind stirring the ingredients of star birth into motion. At the same time, cosmic rays can also heat the gas, preventing it from collapsing too quickly and ensuring that stars form at a steady, sustainable pace. One of the most fascinating aspects of cosmic rays is their ability to influence the chemistry of molecular clouds. When these particles collide with gas, they can break apart molecules, creating new compounds and altering the cloud's composition. This chemical transformation isn't just a curiosity, it's a crucial part of the star-forming process. The molecules created by cosmic rays can act as coolants, helping the gas lose energy and collapse more efficiently. In this way, cosmic rays are like cosmic alchemists, transforming the raw materials of the universe into the building blocks of stars. Cosmic rays also offer us a unique window into the universe's most extreme environments. By studying these particles, we can learn about the supernova, black holes, and other violent events that produce them. They act as messengers, carrying information about the distant corners of the cosmos to our telescopes and detectors here on Earth. This makes cosmic rays not just a part of the star-forming process, but also a tool for understanding the universe itself. The role of cosmic rays in star formation is a reminder that the cosmos is full of hidden forces, quietly shaping the birth and evolution of stars. From ionizing gas to stirring up molecular clouds, these energetic particles are the unseen architects of the universe, weaving the fabric of creation in ways we're only beginning to understand. And as we unravel their mysteries, we gain not just insight into the stars above, but also a deeper appreciation for the intricate, beautiful processes that drive the cosmos. As we zoom out from the birth of individual stars, the cosmic canvas expands to reveal something even more breathtaking: galaxies. These vast, sprawling collections of stars, gas, and dust are the building blocks of the universe, each one a masterpiece of cosmic architecture. But galaxies aren't just random gatherings of stars, they are dynamic systems, shaped by the very processes that give birth to stars. So, how do galaxies form, and what role do stars play in their evolution? The story of galaxies begins in the early universe, just after the Big Bang. At that time, the cosmos was a swirling sea of gas, mostly hydrogen and helium, with tiny ripples of density scattered throughout. These ripples, seeded by the earliest moments of the universe, acted as the starting points for galaxy formation. Gravity, the great sculptor of the cosmos, began to pull these regions of slightly denser gas together, drawing them into clumps that would eventually become the first galaxies. Within these clumps, stars began to form, igniting the first light in the universe. These early stars were unlike anything we see today: massive, hot, and short-lived. They burned brightly and died quickly, seeding the cosmos with heavier elements like carbon and oxygen. This process, known as nucleosynthesis, was crucial for the evolution of galaxies, as it provided the raw materials for future generations of stars and planets. But the birth of stars doesn't just shape galaxies, it's also shaped by them. In the crowded environment of a galaxy, stars are born in dense molecular clouds, often triggered by the gravitational pull of nearby stars or the shockwaves from supernova. These interactions create a feedback loop where the birth and death of stars influence the structure and evolution of the galaxy itself. For example, when massive stars explode as supernova, they can compress nearby gas, triggering the formation of new stars. At the same time, the energy and radiation they release can heat the surrounding gas, preventing it from collapsing and forming stars. Galaxies themselves come in a variety of forms, from the majestic spirals with their swirling arms of stars and gas to the smooth, featureless ellipticals filled with ancient stars. The shape and structure of a galaxy are largely determined by its history of star formation. Spiral galaxies, for instance, are often sites of active star birth, with vibrant, glowing regions where new stars are being born. Elliptical galaxies, on the other hand, are typically older and more settled, with little gas left to fuel new star formation. What's truly fascinating is how galaxies interact with one another, shaping their evolution over billions of years. When two galaxies collide, the gravitational forces at play can trigger bursts of star formation, creating dazzling displays of light and energy. These galactic mergers are some of the most dramatic events in the universe, and they play a crucial role in the growth and evolution of galaxies. The connection between stars and galaxies is a reminder of the interconnectedness of the cosmos. From the smallest spark of a newborn star to the vast, swirling structures of galaxies, the universe is a tapestry of creation, woven together by the forces of gravity, energy, and time. And as we study these grand systems, we gain not just a deeper understanding of the stars above, but also of the intricate processes that shape the universe itself. From the birth of stars to the evolution of galaxies, the cosmic story is one of beauty, complexity, and endless wonder. As we explore the vastness of the universe, there's an invisible force at work, one that's shaping the very fabric of space and time. This force is dark energy, a mysterious and elusive entity that's accelerating the expansion of the cosmos. Unlike gravity, which pulls things together, dark energy seems to push them apart, stretching the universe on the largest scales. While it doesn't directly influence the birth of individual stars, its effects ripple through the cosmos, shaping the environments where galaxies and stars form. So, what exactly is dark energy, and how does this enigmatic force leave its mark on the universe? Dark energy was first discovered in the late 1990s, when astronomers observed that distant galaxies were moving away from us faster than expected. This unexpected acceleration suggested that something was counteracting gravity's pull, driving the universe to expand at an ever-increasing rate. That something is dark energy, a force that makes up roughly 68% of the universe's total energy content. Yet, despite its dominance, dark energy remains one of the greatest mysteries in modern science. We can't see it, touch it, or directly measure it. Its presence is inferred solely through its effects on the cosmos. One of the most profound ways dark energy shapes the universe is by influencing the large-scale structure of galaxies. As the universe expands, the space between galaxies grows, creating vast cosmic voids separated by filaments of matter. These structures, often likened to a cosmic web, are the scaffolding on which galaxies and stars are built. Dark energy doesn't just stretch the universe, it also determines how matter is distributed across it, setting the stage for the birth of celestial bodies. But how does this expansion affect star formation? On smaller scales, like within galaxies, the effects of dark energy are minimal. Gravity still dominates, pulling gas and dust together to form stars. However, on larger scales, dark energy's influence becomes more apparent. As the universe expands, it stretches the distances between galaxies, making it harder for them to interact and merge. Over time, this could slow the growth of massive galaxy clusters, which are often hotspots for star formation. In a sense, dark energy acts as a cosmic brake, gradually shaping the rate at which new stars are born. What's truly fascinating is how dark energy challenges our understanding of the universe. Unlike gravity, which we can describe with Einstein's theory of general relativity, dark energy defies easy explanation. Some theories suggest it's a property of space itself, a kind of energy inherent to the vacuum of the cosmos. Others propose that it's linked to an unknown field or particle waiting to be discovered. Whatever its true nature, dark energy reminds us that the universe is full of surprises and that there's still much we don't understand. The role of dark energy in the cosmos is a reminder that the universe is more than just the sum of its visible parts. It's a dynamic, ever-changing system shaped by forces we're only beginning to comprehend. And as we continue to study this mysterious force, we gain not just insight into the expansion of the universe, but also a deeper appreciation for the intricate, beautiful processes that drive its evolution. From the birth of stars to the structure of galaxies, dark energy is the unseen hand that guides the cosmos, weaving the fabric of the universe itself. The universe is more than just a vast expanse of stars and galaxies. It's a cosmic cradle, nurturing the very ingredients needed for life: carbon, oxygen, nitrogen, and other essential elements. The building blocks of every living thing owe their existence to the fiery hearts of stars. When massive stars explode as supernova, they scatter these elements across the cosmos, seeding the universe with the raw materials for planets, oceans, and ultimately life itself. But how does this incredible journey unfold, and what does it tell us about our own origins? It all begins deep within the cores of stars, where nuclear fusion transforms simple elements into more complex ones. Hydrogen, the most abundant element in the universe, fuses to form helium. In more massive stars, this process continues, creating heavier elements like carbon, oxygen, and nitrogen. These elements are the foundation of life as we know it, essential for everything from the air we breathe to the molecules that make up our DNA. But for these elements to reach us, they must first escape the confines of their stellar nurseries. This is where supernovae come in. When a massive star exhausts its fuel, its core collapses, triggering a cataclysmic explosion. The shock waves from this explosion blast the star's outer layers into space, carrying with them the newly forged elements. These elements are then swept up by molecular clouds, the very same clouds where new stars and planets are born. Over billions of years, this cycle repeats, enriching the cosmos with the building blocks of life. But the journey doesn't end there. Once these elements are incorporated into a molecular cloud, they become part of the raw material for new planetary systems. As a star forms, it's surrounded by a swirling disk of gas and dust, rich in the elements forged by its predecessors. Within this disk, planets begin to take shape, each one a unique blend of these cosmic ingredients. Some, like Earth, gather enough of the right elements to support the complex chemistry needed for life. What's truly remarkable is how interconnected this process is. The carbon in our bodies, the oxygen we breathe, and the nitrogen in our DNA were all created in the hearts of stars, scattered across the universe, and eventually incorporated into our planet. This means that, in a very real sense, we are made of stardust, a living testament to the incredible journey of these elements across space and time. The role of stars in the origins of life is a reminder of the profound connection between the cosmos and our own existence. It's a story that spans billions of years, from the birth of stars to the emergence of life on Earth. And as we continue to explore the universe, we're not just learning about distant stars and galaxies, we're uncovering the story of ourselves, written in the language of the stars. From the fiery cores of stars to the delicate chemistry of life, the universe is a place of endless creativity and possibility. And as we gaze up at the night sky, we're reminded that the stars above are more than just points of light. They are the architects of life, the silent builders of the world we call home. Time is the silent architect of the cosmos, shaping the birth of stars with a patience that spans millions, or even billions of years. Unlike the dramatic explosions and fiery collisions that capture our imagination, the process of star formation unfolds at a pace that's almost unimaginably slow. From the first faint stirrings of a molecular cloud to the moment nuclear fusion ignites, time is the invisible thread weaving the story of every star. But how does this cosmic clock influence the journey from gas and dust to blazing stellar bodies? Let's start with the collapse of a molecular cloud. This initial phase, where gravity begins to pull gas and dust together, can take millions of years. It's not a sudden event but a gradual process where tiny fluctuations in density grow over time, eventually reaching a tipping point. Think of it like a snowball rolling down a hill. It starts small, almost imperceptibly slow, but as it gathers momentum, it becomes unstoppable. The same is true for star formation. Time allows gravity to work its magic, slowly but surely compressing the cloud into the dense cores that will one day ignite as stars. Once a protostar forms, time continues to play a critical role. The young star grows by accreting material from its surrounding disk, a process that can take tens of thousands of years. During this phase, the star's core heats up, inching closer to the temperatures needed for nuclear fusion. But fusion doesn't happen overnight. It's the result of countless collisions and reactions, each one building on the last. It's a cosmic countdown where time is the measure of progress, ticking away until the star finally bursts into life. What's fascinating is how time influences the diversity of stars. A massive star, for example, burns through its fuel in just a few million years, living fast and dying young. In contrast, smaller stars like red dwarfs can take billions of years to form and may shine for trillions of years, their lives unfolding at a glacial pace. This contrast in timescales isn't just a curiosity, it's a key factor in the evolution of galaxies and the distribution of elements throughout the universe. Time also leaves its mark on the environments where stars are born. In regions of active star formation, like spiral arms of galaxies, the interplay between gravity, turbulence, and radiation creates a dynamic timeline. Some stars may form quickly, triggered by shock waves from nearby supernova, while others take longer, growing slowly in quieter pockets of the cloud. This variability in timing ensures that star formation is never a one-size-fits-all process. It's a symphony of events, each one playing out on its own unique schedule. What can we learn from the cosmic timeline? For one, it teaches us patience. The processes that shape the universe don't conform to human timescales. They operate on a grand, almost incomprehensible scale. Yet, by studying these processes, we gain insight into the fundamental forces that govern the cosmos. Time isn't just a measure of change. It's a window into the universe's history, revealing how stars, galaxies, and even life itself came to be. As we gaze at the night sky, we're not just seeing stars, we're witnessing moments in a story that began billions of years ago and will continue long after we're gone. The cosmic clock keeps ticking, shaping the universe in ways that are both profound and beautiful. And in understanding the role of time, we come to appreciate the incredible patience and precision of the forces that bring stars to life. In the earliest moments of the universe, before galaxies, before planets, and before even the faintest glimmers of light, there was darkness. But within that darkness, something extraordinary was brewing: the birth of the first stars. These stars, known as population Roman 3 stars, were unlike anything we see today. They were the pioneers of the cosmos, born from the pure, primordial gas left over from the Big Bang, a gas made almost entirely of hydrogen and helium with no trace of heavier elements. So, how did these first stars come to be? The story begins in the aftermath of the Big Bang, when the universe was a hot, dense soup of particles. As it expanded and cooled, tiny ripples in the cosmic fabric began to grow, regions where matter was slightly denser than the surrounding space. Over hundreds of millions of years, gravity pulled these denser regions together, forming the first clumps of gas. These clumps, isolated in the otherwise uniform expanse of the early universe, became the seeds of the first stars. What made population Roman 3 stars so unique was their sheer size and power. Without the heavier elements that help cool and fragment gas clouds in modern star formation, these primordial stars grew to enormous masses, some as much as 100 times the mass of our Sun. Their cores burned at incredible temperatures, driving nuclear fusion at a furious rate. Yet their brilliance came at a cost. These massive stars lived fast and died young, burning through their fuel in just a few million years before exploding as supernovae. But their short lives had a profound impact on the cosmos. When these stars exploded, they scattered the first heavy elements, carbon, oxygen, and others, into the surrounding gas. These elements, forged in the hearts of population Roman 3 stars, became the building blocks for future generations of stars, planets, and even life itself. It's a cosmic legacy that continues to shape the universe today. Studying these ancient stars isn't just about understanding the past, it's about unlocking the secrets of the early universe. Because population Roman 3 stars were so massive and bright, they played a key role in ending the cosmic dark ages, a period when the universe was filled with neutral hydrogen and no stars had yet formed. Their intense radiation ionized the surrounding gas, clearing the way for light to travel freely and setting the stage for the formation of galaxies. Yet, despite their importance, population Roman 3 stars remain elusive. Because they lived and died so long ago, we've never directly observed one. Instead, astronomers rely on clues from their remnants, the heavy elements they left behind, and the faint echoes of their radiation. These clues, combined with advanced simulations, allow us to piece together the story of these cosmic pioneers. The birth of the first stars is a reminder of how far the universe has come. From a dark, featureless expanse to a cosmos filled with light, stars, and galaxies, the journey began with these ancient giants. They were the first to ignite the darkness, the first to forge the elements of life, and the first to set the universe on the path to becoming the vibrant, diverse place we see today. And as we uncover their secrets, we're not just learning about the stars, we're uncovering the story of the universe itself. For centuries, humans gazed at the night sky with wonder, piecing together the mysteries of the cosmos using little more than their eyes and imagination. But today, our understanding of star formation has been transformed by something extraordinary: technology. From powerful telescopes that peer into the depths of space to advanced supercomputers that simulate the birth of stars, these tools have opened doors to discoveries that once seemed impossible. They've allowed us to see beyond the visible, to uncover the hidden processes that shape the universe, and to ask questions that push the boundaries of our knowledge. So, how exactly has technology reshaped our understanding of star formation? And what lies ahead as we continue to push the limits of innovation? Let's start with the tools that bring the cosmos into focus: telescopes. Modern observatories, both on Earth and in space, have revolutionized our ability to study star-forming regions. Take, for example, the Hubble Space Telescope, which has captured breathtaking images of glowing nebulae and swirling molecular clouds. These images aren't just beautiful, they're scientific goldmines, revealing the structure and composition of the clouds where stars are born. But Hubble is just the beginning. Telescopes like the James Webb Space Telescope, with its infrared capabilities, can peer through the dust that obscures star-forming regions, giving us an unprecedented view of the earliest stages of stellar birth. On the ground, radio telescopes like ALMA, the Atacama Large Millimeter/Submillimeter Array, have taken things even further. By detecting radio waves emitted by molecules in molecular clouds, ALMA allows us to map the distribution of gas and dust with incredible precision. This has given us insights into the dynamics of star formation, showing how turbulence, magnetic fields, and gravity interact to shape the birth of stars. It's like having a front row seat to the cosmic drama, watching the process unfold in real time. But technology doesn't just help us observe the universe, it also lets us recreate it. Supercomputers have become indispensable tools for simulating the complex processes of star formation. These machines can model the collapse of molecular clouds, the formation of protostars, and even the ignition of nuclear fusion, all with stunning accuracy. By running these simulations, scientists can test theories, predict outcomes, and uncover patterns that might otherwise go unnoticed. It's a way of experimenting with the universe, exploring scenarios that are too vast, too distant, or too extreme to study directly. One of the most exciting developments in recent years has been the rise of machine learning and artificial intelligence in astronomy. These technologies are helping researchers sift through massive datasets, identifying patterns and anomalies that might otherwise be missed. For example, AI algorithms can analyze images from telescopes to spot newborn stars or predict where star formation is likely to occur next. This not only speeds up the research process, but also opens up new avenues for discovery, allowing us to explore the cosmos in ways we never thought possible. Looking to the future, the possibilities are endless. New telescopes like the extremely large telescope ELT under construction in Chile promise even greater resolution and sensitivity, allowing us to study star formation in unprecedented detail. Meanwhile, advancements in computing power and AI will continue to enhance our ability to model and understand the universe. The next generation of space missions, such as the Nancy Grace Roman Space Telescope, will further expand our view, offering new insights into the birth of stars and the evolution of galaxies. Technology has not only deepened our understanding of star formation, but also transformed the way we see ourselves in the universe. Each new discovery reminds us of the incredible complexity and beauty of the cosmos, while also highlighting how much we still have to learn. As we continue to push the boundaries of innovation, one thing is certain: the tools we create will not only reveal the secrets of the stars, but also inspire us to dream bigger, to explore further, and to uncover the mysteries that lie beyond the horizon. From the telescopes that bring the cosmos into focus to the supercomputers that simulate its secrets, technology is the lens through which we view the universe. And as we look to the future, we're reminded that the journey of discovery is just beginning. A journey driven by curiosity, creativity, and the relentless pursuit of knowledge. Picture the universe in the far, far future, trillions of years from now. The stars we see today have long since faded, their light extinguished, their energy spent. In this distant era, the cosmos is filled with the remnants of stars, cold and dark, drifting silently through the void. Among these remnants are black dwarfs, the hypothetical final stage of stellar evolution. These objects are the ultimate endpoint for stars like our Sun, a quiet conclusion to a life that once burned brightly. But what exactly are black dwarfs, and why do they remain purely theoretical? Let's unravel the story of these cosmic shadows and what they reveal about the fate of stars. Black dwarfs begin their journey as white dwarfs, the dense, Earth-sized remnants of low-mass stars that have exhausted their nuclear fuel. Over billions of years, white dwarfs slowly cool, radiating away their remaining heat into space. But the process of becoming a black dwarf is unimaginably slow. It takes trillions of years, far longer than the current age of the universe, for a white dwarf to cool to the point where it no longer emits any significant light or heat. At that stage, it becomes a black dwarf, a cold, dark object that blends seamlessly into the cosmic background. What makes black dwarfs so fascinating is their role as cosmic time capsules. By the time a white dwarf cools into a black dwarf, the universe itself will have undergone profound changes. galaxies will have expanded and faded, new stars will have ceased to form, and the universe will be a much darker, colder place. Black dwarfs, in a sense, are the silent witnesses to this cosmic twilight, carrying with them the history of stars that once illuminated the cosmos. But why don't black dwarfs exist yet? The answer lies in the timescale of their formation. The universe is currently only about 13.8 billion years old, far too young for even the oldest white dwarfs to have cooled into black dwarfs. In fact, the first black dwarfs aren't expected to appear for at least another 10 to the power of 15 years, a number so large it's almost impossible to comprehend. This means black dwarfs remain a theoretical concept, a glimpse into the distant future of stellar evolution. What can black dwarfs teach us about the ultimate fate of stars? For one, they highlight the incredible longevity of stellar remnants. Even after a star's light has faded, its legacy endures in the form of these cold, dark objects. They also remind us of the dynamic nature of the universe, where even the most enduring structures, stars, galaxies, and even black holes, are subject to change over unimaginable timescales. Black dwarfs are a testament to the slow, inexorable march of time, a reminder that the cosmos is always evolving, even in ways we can't yet observe. The story of black dwarfs is more than just a scientific curiosity. It's a window into the far future of the universe. As we ponder these cold, dark remnants, we're reminded of the vastness of cosmic time and the delicate balance that governs the life and death of stars. And while black dwarfs may remain elusive for now, they offer us a glimpse of what lies ahead, a quiet ending to the grand story of stellar evolution. From the fiery birth of stars to their cold, dark demise, the universe is a place of endless transformation, where even the faintest embers hold the secrets of eternity. At the heart of every discovery, every telescope pointed skyward, and every question asked about the cosmos lies something profoundly human: curiosity. It's this relentless drive to understand, to explore, and to connect with the universe that has propelled us from stargazing on ancient plains to launching spacecraft into the farthest reaches of space. Curiosity isn't just a trait, it's the engine of exploration, the spark that ignites our journey into the unknown. And when it comes to the mysteries of the universe, from the birth of stars to the origins of life, curiosity has been our most powerful tool. Think about the first time someone looked up at the night sky and wondered, what are those points of light? That simple question, born of curiosity, has led to centuries of observation, experimentation, and discovery. From Galileo's first telescopic observations to the Hubble Space Telescope's breathtaking images of distant galaxies, our understanding of the cosmos has been shaped by the questions we've dared to ask. Each discovery builds on the last, creating a tapestry of knowledge that continues to grow with every generation. But curiosity isn't just about asking questions, it's about the courage to pursue answers even when the path is uncertain. Take, for example, the story of Henrietta Swan-Leavitt, an astronomer whose curiosity about variable stars led her to discover a relationship between their brightness and distance. Her work laid the foundation for measuring cosmic distances, transforming our understanding of the scale of the universe. It's a reminder that curiosity, paired with perseverance, can unlock doors we didn't even know existed. What's truly remarkable is how curiosity connects us across time and space. When we study the birth of stars or the formation of galaxies, we're not just learning about distant objects, we're uncovering the story of our own origins. The carbon in our bodies, the oxygen we breathe, and the very atoms that make up our world were forged in the hearts of stars. In exploring the cosmos, we're also exploring ourselves, tracing the threads that bind us to the universe. Curiosity also has a unique way of bringing people together. From ancient astronomers tracking the movements of planets to modern-day collaborations involving thousands of scientists, the quest to understand the cosmos has always been a shared endeavor. It's a reminder that no matter where we come from or what challenges we face, we're united by our desire to explore and understand the world around us. As we reflect on the role of curiosity in our cosmic journey, it's worth asking, what drives us to keep exploring? Perhaps it's the thrill of discovery, the joy of uncovering something new. Or maybe it's the sense of wonder that comes from realizing just how vast and intricate the universe truly is. Whatever the reason, one thing is clear: curiosity is more than just a trait. It's a force, a guiding light that leads us ever forward, deeper into the mysteries of the cosmos. And as we continue to explore, we're reminded that the journey is just as important as the destination. Every question we ask, every discovery we make, brings us closer to understanding not just the universe, but also our place within it. So, the next time you look up at the night sky, take a moment to embrace that sense of wonder. Because in that moment, you're not just an observer, you're part of a timeless journey driven by the same curiosity that has shaped our understanding of the stars for millennia. Long before Earth or the Sun existed, the story of our solar system began in the cold, dark embrace of a vast molecular cloud. This cloud, a swirling sea of gas and dust, was the birthplace of everything we know today: our sun, the planets, and even the materials that make up life itself. The formation of the solar system is a cosmic tale that mirrors the birth of stars across the universe, offering us a front-row seat to the processes that shape celestial bodies. But how did this familiar system of planets and a star come to be? And what does it reveal about the broader story of star formation? The journey to the solar system's creation started around 4.6 billion years ago, when a small region within the molecular cloud began to collapse under its own gravity. This collapse wasn't random. It was triggered by a shock wave, possibly from a nearby supernova or the gravitational tug of a passing star. As the cloud contracted, it began to spin faster, flattening into a rotating disk known as the protoplanetary disk. At the center of this disk, material accumulated, growing hotter and denser until nuclear fusion ignited, and the sun was born. But the sun wasn't alone. Surrounding it was a swirling expanse of gas and dust, the raw materials for the planets. Within this disk, tiny grains of dust collided and stuck together, forming pebbles, then rocks, and eventually planetesimals, the building blocks of planets. Over millions of years, these planetesimals merged through collisions and gravitational attraction, growing into the protoplanets that would become the worlds we know today. What's fascinating about this process is how it mirrors the formation of other star systems. The solar system is a microcosm of star formation, a small-scale example of the same forces that shape galaxies across the universe. The Sun's protoplanetary disk, for instance, is similar to the disks we observe around young stars in distant nebulae. These disks are the cosmic cradles where stars and planets take shape, and studying our own solar system gives us a unique opportunity to understand this universal process in detail. The solar system also teaches us about the diversity of planetary systems. While our system has 8 planets, each with its own unique characteristics, other star systems can look very different. Some have gas giants orbiting close to their stars, while others have planets so small and dense they defy our expectations. This variation is a reminder that star formation isn't a one-size-fits-all process. It's a dynamic, unpredictable journey that produces a stunning array of outcomes. But perhaps the most profound lesson from the solar system's formation is its connection to life. The heavy elements that make up Earth, carbon, oxygen, nitrogen, and others, were forged in the hearts of ancient stars and scattered by supernova. These elements became part of the molecular cloud that gave birth to the Sun and its planets, eventually forming the building blocks of life. In this way, the solar system isn't just our cosmic home, it's a testament to the incredible chain of events that brought us into existence. The story of the solar system is a reminder of the intricate, beautiful processes that shape the universe. From the collapse of a molecular cloud to the formation of planets, it's a journey that spans billions of years and connects us to the cosmos in profound ways. And as we continue to explore our own solar system and beyond, we're not just uncovering the secrets of the stars, we're discovering the story of ourselves, written in the language of the universe. The universe is vast, its mysteries complex, and its secrets hidden in the farthest reaches of space. To uncover these secrets, no single mind or nation could ever hope to go it alone. The study of star formation, like all great scientific endeavors, is a testament to the power of collaboration. From the engineers who design cutting-edge telescopes to the scientists who analyze the data, and even the enthusiasts who share their passion for the cosmos, it's through teamwork that we've made some of the most profound discoveries about the birth of stars. But what makes collaboration so essential to exploring the universe, and how does this collective effort shape our understanding of the cosmos? Take, for example, the James Webb Space Telescope, one of humanity's most ambitious projects. This marvel of engineering didn't come to life in a vacuum. It was the result of decades of work by thousands of people from multiple countries, each contributing their expertise. Engineers designed its intricate systems, astronomers planned its observations, and countless others ensured its success from launch to deployment. Without this global effort, we wouldn't have the breathtaking images and groundbreaking data that Webb continues to provide, revealing the earliest stages of star formation in unprecedented detail. Collaboration also extends beyond the confines of laboratories and observatories. International partnerships like those between NASA, ESA, and other space agencies have been instrumental in advancing our knowledge. By pooling resources, sharing technology, and combining expertise, these collaborations allow us to tackle questions that would be impossible to answer alone. For instance, the Atacama Large Millimeter/Submillimeter Array ALMA, a network of radio telescopes in Chile, is a joint effort involving over 20 countries. Its ability to peer through cosmic dust and map the intricate structures of star-forming regions has revolutionized our understanding of how stars are born. But collaboration isn't just about large-scale projects or formal partnerships. It's also about the countless individuals, amateur astronomers, educators, and citizen scientists who contribute to the field in their own unique ways. Amateur astronomers armed with modest telescopes and a passion for the night sky have discovered comets, tracked variable stars, and even identified new star-forming regions. Meanwhile, citizen science projects like Galaxies invite people from all walks of life to help classify galaxies, contributing to research that professionals simply couldn't accomplish alone. What's truly remarkable about collaboration is how it amplifies our collective potential. By working together, we can approach problems from multiple angles, combining diverse perspectives and skills to find innovative solutions. This synergy is what drives progress, pushing the boundaries of what we know and inspiring new questions to explore. It's a reminder that science isn't just about individual brilliance, it's about the shared pursuit of knowledge, the willingness to learn from one another, and the commitment to a common goal. As we continue to explore the cosmos, collaboration will remain at the heart of our journey. Whether it's through international missions, citizen science initiatives, or the simple act of sharing knowledge, every contribution brings us closer to understanding the universe. And in this shared endeavor, we're reminded of something profound, that the quest to uncover the mysteries of star formation isn't just about the stars themselves. It's about the connections we forge, the discoveries we make together, and the collective wonder that unites us all. So, the next time you gaze at the night sky, remember that the light you see is not just a product of cosmic processes, it's also a reflection of the countless minds and hands that have come together to bring its secrets into the light. Collaboration is the thread that weaves through the fabric of discovery, a testament to what we can achieve when we work together to explore the boundless wonders of the universe. From the silent collapse of molecular clouds to the dazzling ignition of nuclear fusion, the birth of stars is a tale of cosmic artistry and profound significance. Over the course of this journey, we've uncovered 10 fascinating insights into how stars ignite and transform the universe. We've seen how gravity pulls the threads of gas and dust together, how magnetic fields sculpt the chaos of star-forming regions, and how the explosive deaths of massive stars scatter the building blocks of life across the cosmos. Each step in this process is a testament to the intricate, interconnected forces that shape the universe. Stars are more than just distant points of light, they are the engines of creation. They forge the heavy elements that make up planets, moons, and even life itself. Their light illuminates the darkest corners of space, guiding us as we explore the mysteries of the cosmos. And their legacy endures long after their light fades, woven into the fabric of galaxies and the story of the universe itself. But the story of star formation is far from over. With every new discovery, every image captured by our telescopes, and every simulation run by our supercomputers, we uncover new layers of complexity and beauty. The universe is a living, evolving tapestry, and stars are its most vibrant threads. As we continue to study these celestial wonders, we're reminded of how much there is still to learn and how much there is to marvel at. Thank you for joining us on this journey through the birth of stars, a journey that has taken us from the depths of molecular clouds to the fiery hearts of supernova. If you've enjoyed exploring these cosmic mysteries with us, don't forget to like, subscribe, and share your thoughts in the comments below. Your curiosity and enthusiasm inspire us to keep exploring, keep learning, and keep sharing the wonders of the universe. Until next time, keep looking up at the stars, because every time you do, you're connecting with the forces that shape the cosmos and in turn shaped us. The universe is vast, beautiful, and full of stories waiting to be told. Let's keep discovering them together.